Thank you. I will share my screen. Yeah, thank you so much for inviting. I am from Scandinavia, so like neighboring country. I will speak about a recent project with Alessio D'Alì. He's from the University of Osnabrück in Germany. The title of my talk is Gorenstein algebras from simplicial complexes. But before we dive into the subject, please let me tell you that anytime you have questions or comments or remarks or anything that is not clear, please feel free to interrupt anytime. I will be very happy to make this as interactive as possible. Okay. So I want to sort of start from the end, in the sense that before giving any sort of details, I want to convey the idea that what this project was actually about. So we study a construction that associates to any pure simplicial complex. So a simplicial complex, I will explain every single word, but pure simplicial complex, you can think of it as a geometric, maybe topological object. And we are going to do a two-steps construction. So we are going to turn this object into something called the beer ball associated to delta. Then we are going to apply idealization. So this is another black box for now. And this construction is going to spit out an algebra, which I will denote with R sub delta. This algebra is Gorenstein and graded. Okay. Again, everything will be explained. The results of our project are to relate properties of delta to the properties of the algebra. So properties of a geometric topological object to the properties of an algebraic object. And we are going to, at the end of the day, we're going to show a couple of if and all ifs. So this property holds for delta, if and all ifs, this other property holds for the algebra. Okay. So this is the message that you should take home from my talk. Now we start with a little bit of details. So I'm starting from the very basics. Please speed me up if it's too basic, or slow me down if it's not. So during my talk, S will denote the polynomial ring in n variables. K, I don't make any assumption on K for now. I will consider graded K algebras. So these are simply quotients of the form S mod I, where I is an homogeneous ideal for some grading. And when I say that the algebra is standard graded, then I will simply mean that the variables get degree 1, which is probably what you expect them to get. Once I have a graded algebra, I can consider or maybe like, let's say a standard graded algebra, I can consider the Hilbert function. So this is a function from n to n, which associate to I the dimension of the K vector space given by all homogeneous elements of degree I in R. Okay, so R sub I is the space of all homogeneous elements of degree I. It's very classical to do some generating functions with it. So to plug in the Hilbert function into this power series. So we take the infinite sum of the Hilbert function t to the I, and it's a classical theorem that this can be represented as a rational function. This is a rational function. And at the denominator, I have 1 minus t to a certain power. And if I make sure that the polynomial at the numerator is not divisible by 1, then this defines, well, first of all, the numerator polynomial, and this number d, okay? So once I divide out all the powers, all the 1 minus t factors that I can, this defines d, okay? So d is called the crude dimension of the algebra, while the numerator is called the h polynomial of the algebra, or like if I want to just consider the coefficients, which is the same piece of information, this is the h vector of the algebra, okay? So all of these numbers are actually integers, okay? So integer numbers, and I'm using S to denote the actual degree of this polynomial. So let me assume that HS is actually not 0. Okay. This is all very standard. Something else that we can do to extract numerical information from a graded algebra, or more specifically for a graded module over an algebra, is we can consider the graded minimal free resolution. Okay, what is this? So we take a graded S module M, and then we find a long exact sequence, which is actually exact, okay, as I said, in which all the modules in the sequence are free, okay? So they are a direct sum of certain copies of S. And they are shifted in degree in a way such that the linear maps in this sequence are matrices of homogeneous elements of positive degree. So the fact that I'm requiring the matrices in this sequence to have positive degree has to do with the word minimal, because in principle you could have scalars in the matrices, but if I require the elements to have strictly positive degree, then this resolution is minimal, and it becomes somehow unique up to isomorphism of chain complexes. So again, it defines something. And what it defines these numbers here, which are the numbers beta ij, and those are called the graded Petit numbers. So beta ij is the number of summands of the S minus j shifted copy in Fi. Okay. And I'm going to use graded minimal free resolution to define two classes of algebras that will be of interest for my talk today. The first one is Cohen-Macaulay algebras. I will say that an algebra S mod I of dimension D, so this is crude dimension D, is Cohen-Macaulay over K. So this depends on the field. If the number PD of R, which stands for projective dimension, is n minus t. So I didn't tell you what is PD of R, but you might have noticed it from the sequence. So this is the index of the last non-zero module in the graded minimal free resolution. So in some sense, it's the length of the graded minimal free resolution. Okay. So we are saying that an algebra is Cohen-Macaulay if this length is actually equal to the number of variables in the polynomial ring S minus the crude dimension. Okay. This is actually the shortest that graded minimal free resolution of an S module can be, of crude dimension D. A subclass of Cohen-Macaulay algebras is Gorenstein algebras. We say that an algebra is Gorenstein over K if it is Cohen-Macaulay, and the rank of the last module is 1. Okay, so we require something very specific, that the last module has rank 1. Okay. Actually, if you are geometrically inclined, maybe geometrically in the sense of algebraic geometry, you might want to add a further subclass of Gorenstein algebras, which is complete intersections. So complete intersections also do satisfy this property, but they are very strictly contained in Gorenstein algebras. Okay. So I spent some time telling you about numerical invariance of the algebras, like the H vector. So let me tell you some special property of the H vector for these two classes. Well, for the first one, for Cohen-Macaulay algebras, the integers and the integer entries in the H vector are non-negative numbers. And one way to see that they are is that you can actually figure out that they count something. So they count monomials in a certain multi-complex. So in particular, they are non-negative integers. Furthermore, if we consider the H vector of a Gorenstein algebra, they have an interesting symmetry. So they are, I will say that they are palindromic. So remember that we had numbers from H0 to HS. Palindromic means that the ith number is equal to the S minus ith. So there is symmetry in this sequence. This will play a role in a couple of slides. Okay, so I told you something about the algebraic object. Now let me switch briefly to the geometric one, so simplicial complexes. For me, a simplicial complex will be, I will treat simplicial complexes abstractly, so just collection of subsets close to under inclusion. And the dimension of a simplicial complex is the maximum of a cardinality of an element of a simplicial complex. And there's -1. So this shift of -1 is just to encode the fact that, you know, 3 vertices, they build up a triangle, and this has dimension 2 and not 3. Again, we have numerical invariance for simplicial complexes as for algebras. In particular, the most obvious thing to do is to store the number of faces in each dimension in a vector. This is called the F vector. So if I counts the number of faces of dimension I, or equivalently of cardinality I plus 1. So this is a first bridge from simplicial complexes to algebra. You probably have already heard of it. This is, by the way, not the construction that I presented in the very first slide, that I mentioned in the very first slide, but it's going to be important. So this is the Stanley-Reisner ring of delta. What we can do, we can associate to delta a square-free monomial ideal, I sub delta, and this square-free monomial ideal is generated by all the products of monomials, which are supported on something that it's not a phase of delta. So here's the first type of the day. There's going to be more. Hopefully not. So those are products of variables, and the index runs through all phases which are not phases of delta. Okay. And I define the H vector of delta, the H vector of the Stanley-Reisner ring of delta. Okay. So this is the coefficients that you see in the numerator of the Hilbert series of this algebra. A class of simplicial complexes that will be important today is flag simplicial complexes. The best way to define them, since I just told you what the Stanley-Reisner ring is delta is flag if the ideal I of delta is generated in degree 2. So in other words, every time I find a face, I find a subset of the vertices that is not a face. The reason why this is not a face is that there is a pair of vertices in this subset that is not connected by an edge. So minimal non-faces have cardinality 2. There's another interesting way to define this class of complexes is that they are equal to the complex of cliques of its graph. Okay, so if I take a simplicial complex, this naturally has a graph, so given by edges and vertices. I can take the graph, and then I can fill in all complete subgraphs, so all cliques. And this will give me back a simplicial complex. That there is no reason why I should get back the simplicial complex that I started from. And but when I do, the simplicial complex is called flag. Okay, and one last tool to work with simplicial complexes is the link of a face in delta. This is another simplicial complex which describes the local behavior of delta around F. And more precisely is given by all faces of delta, which they do not intersect F. So F is the special phase that I'm looking at. But if I take the union with F, then I obtain a face of the simplicial complex. Okay, so this is really the discrete neighborhood of a face in the simplicial complex. So you might be very used to everything I said so far, but this might be a new piece of information for some of you. So this looks like magic to me. So I'm gonna describe something called beer balls. And it's a very, very simple construction, which to every simplicial complex on n vertices, like without any assumption, spits out a triangulated ball. So a simplicial complex that is a ball on 2n vertices. Okay. And again, I will define, so I call delta the arbitrary simplicial complex, and gamma, the ball that we will obtain at the end of the day. And I will define gamma via the Stanley-Reisner ideal. So the Stanley-Reisner ideal of gamma is simply that of delta by adding xi, yi for every y in n. So you see that I am re-embedding I of delta into a polynomial ring with 2n variables. So from xy to xn and from y1 to yn. But I don't only consider the generators in I of delta, which for me, remember, they had the letter x. So x were the variables appearing in I of delta. But now I'm adding all the pairs xi times yi. So this is a very simple construction. And it turns out that if you look at this defines a simplicial complex, because this is a square-free monomial ideal. I didn't tell you, but there is a correspondence between square-free monomial ideals and simplicial complexes. And it turns out that gamma is a ball, is a n-1 dimensional ball, which is a boundary complex, which is a subcomplex of the boundary complex of the cross polytope in the same dimension. Okay, I will comment on the picture in a second, so hopefully this will become a little clearer. Let me add a few more properties.
Can I ask a short question?
Yes, of course.
So, I mean, it's kind of two questions. The first one is, there are also things called Beer spheres. Is there some relation between those except for the name?
Yes, those are the boundary of the complexes that I'm considering.
Okay, okay.
Yeah.
And so for the Beer spheres, at least the construction that I know is kind of very geometric in some sense, because you take like the join with the Alexander dual. Is there some kind of geometric construction of beer balls as well?
Well, there should be. So the construction that, yeah, with these deleted joints, I think they are called, or something like that, with the Alexander dual. Yes, there is. I don't know on top of my head how to relate it to the geometric construction, but there should be, like, fairly easily. One can probably sit down and write it on paper.
Okay.
Yeah.
Thanks.
You're welcome. Yeah. Let me do a very easy remark. So since I'm adding monomials of degree 2 to I of delta, well, if delta is flag, if and only if gamma is, right? So if there is a generator which has degree, minimal generator which has degree higher than 2, then it must already be on I of delta. So a property that I will skim over a little bit is that the Stanley-Reisner ring of gamma is a level ring. So, well, essentially, this means that the last module in the minimal free resolution, we're not that lucky that we have a module of rank 1, but we can find a module that is generated in a single degree. So that is shifted in a unique degree. So it's in some sense, it's a generalization of the Gorenstein property, and it's a technical tool that that we will need. But as I said, I'm not going to get into details. Something very nice is that the H vector of delta, the H vector of gamma is the F vector of delta. So there is this swapping between the F vector of one and the H vector of the other. Okay. Yeah, I said I will comment on the picture. So here I took a ridiculously stupid simplicial complex delta. So it's made up of 3 vertices and 1 edge. So what happens if I enlarge the Stanley-Reisner ideal of delta to that of gamma? Well, I'm going to add 3 variables, y1, y2, and y3. And by adding these generators, you can check that the simplicial complex I obtain is the following. So it's this triangulated hexagon. And the first sentence, what I meant with the first sentence is that you can actually see these as a subcomplex of the octahedron. Okay. So the the two-dimensional cross polytope. For me, this means the boundary of the three-dimensional cross polytope. It's the boundary of the octahedron, and you can see this as a subcomplex of that. Okay. Actually, now I have a disclaimer because I was just asked by Patrick that there are Beer spheres, and I think it's way more common in the literature to find Beer spheres rather than Beer balls. This is just a definition we made up to stick to the literature. And if you are in a German country and you Google for Beer ball, you actually find a drinking game. So don't do that, or maybe do that, but not during working hours. Yeah, so my suggestion, of course, is to Google for it because it's fun. Okay, so I told you what Cohen-Macaulay means for a ring. We can easily, we can translate this into simplicial complexes by declaring that delta is Cohen-Macaulay if its Stanley-Reisner ring is a Cohen-Macaulay ring. But if we don't want to go through algebra, we can use a criterion by Reisner, which gives a very simple homological description of what it means for a Cohen-Macaulay complex, for what it means to a simplicial complex to be Cohen-Macaulay. And the description is the following. So delta is Cohen-Macaulay if and only if the homology of all links vanishes everywhere, but possibly in top degree. Okay, so top degree means the degree equal to the dimension. So I take any face, I look at the link is gonna be k dimensional. Then a criterion in order to have Cohen-Macaulayness is to have the homology vanishing everywhere, but it's allowed to have something in top degree. Okay, and this must be true for every face, and this is just the quantifier that I try to explain. So it has to vanish for every homological degree smaller than the dimension. So if you do a little bit of tricks with like basic algebraic topology tools, you will figure out that triangulated balls, so simplicial balls, and spheres are actually Cohen-Macaulay complexes. But we can also filter this property. We can filter this property by setting a threshold below which homology should vanish, but above which it does not. So it's free to do whatever it wants. And this leads to the definition of Serre's properties. So we say that delta satisfies Serre property as S sub R. So here there's an integer R fixed. If for every face, the homology of the link of the face vanishes everywhere, but for every degree, which is lower than the minimum of the dimension of the link, or R minus 1, where R is the threshold that it's fixed. Okay, so essentially we are saying, take your face, look at the link. If the dimension is large enough, this threshold is gonna probably play a role. So you're gonna have some freedom in homology in the top degrees. If the dimension of the link is so small that you stay below the threshold, then you still need to satisfy the only top homology cannot vanish.
Lorenzo, so how do you read the SR property in the Stanley-Reisner ring?
Yeah, very good question. So you read it from the depth of the associated primes. You read that from the depth of the associated primes. Now I don't recall the precise statement, but I think I can figure it out. Just give me a second. So I think that the depth no, I can't figure it out. I will think about it and tell you later. It's encoded in the depth of the associated primes.
Okay, thanks.
Yeah, you're welcome. And the reason why I'm saying that this SER property filters the Cohen-Macaulay property, it's made precise by this chain of implication. So S1, satisfying the property S1, so I'm fixing a very, very low threshold. This is something that all simplicial complexes satisfy. But S2 is already getting a little more interesting. So a simplicial complex satisfies property S2 if and only if it is pure. I didn't tell you what pure means, but pure means that all facets, so all inclusion maximal faces have the same dimension. And the link of a face has to be connected wherever it can be connected. So codimension 1 faces will always have like points as its link. So we cannot really require those to be connected. But for faces of codimension lower than codimension higher than 1, then those links have to be connected. And if we go back, if we go like S3, S4, S5, and we reach S, the dimension of delta plus 1, then this is precisely the class of Cohen-Macaulay complexes. Okay. And actually, it's interesting because at some point between S2 and S dimension of delta plus 1, there's the dependence of the field, which starts to play a role, right? Because the Cohen-Macaulay property depends on the field. The S2 property does not, because it's a statement about connectedness. And at some point in between, the dependence of the field starts to kick in. Examples, as always. The bow-tie complex, it's a simplicial complex, so this is S1. If you believe what I said, it has the S1 property, but it does not have the S2 property because the link of the special vertex is to these joint edges. So it is not connected. The simplicial complex in the middle is a triangulation of the real projective space. It is S2. It is S2 because it's a triangulated surface, but having the S3 property, which in this case coincides with S dimension of delta plus 1, that is to say the Cohen-Macaulay property, holds if and only if the characteristic of the field is 2. And on the last complex, I just have a very basic triangulated ball. So this is Cohen-Macaulay. Okay. Are there questions at this point? Okay. Then again, we switch to the algebra. As I said, we want to control properties of the algebra R of delta with properties of the simplicial complex. So this is the most important property that we want to have control on. We say that this is called Koszul property. We say that a greater algebra R is Koszul over the field K, so it's a K algebra. If the resolution of the residue field, so the residue field is a module, is an R module, is linear. Linear meaning that the graded Betti numbers, they vanish whenever J is strictly greater than I. Okay. So I understand it's quite a statement to parse if you have not heard of it before. We are defining families of algebra if the residue field has a nice, in some sense, linear to be precise, resolution as an R module. Okay. And again, we are gonna filter this condition. We're gonna relax this condition by saying that R as an R step linear resolution. Okay, this is another typo. What I wanted to say here is that K as an R step linear resolution as an R module if the graded Betti number vanish again for every j greater than I, but this time we just ask this vanishing for homological indices smaller than R. Okay, so let me go to an example just to explain what's going on. So I take this quotient here. So this is actually a Stanley-Reisner ring. Stanley-Reisner ring of 2 points. And I compute the resolution of the field K as an R modulo. And you will figure out that the resolution looks like this. So I claim that this, well, this is actually infinite, because something that I didn't lie, but I didn't tell you at the very beginning is that if we consider resolutions over the polynomial ring, then this will be finite. So we are, at some point there will be a 0 here and we are good. But over arbitrary rings for like this one, minimal free resolutions do not need to be finite. But you see the pattern here. This is gonna go on forever, like R minus 4 squared and so on. And this is telling us that it looks very plausible that this algebra is Koszul, because the condition of the resolution being linear is saying that the only Betti number that is allowed to be non-zero here is 0, 0, which is actually correct because this module has shift in degree 0. So beta 0, 0 is 1 and everything else is not there. This one as well, we are having things in degree 1, 1. So shifted in degree 1 and in homological position 1. And it doesn't really matter what this number is. Now it's a 2, but it's important that there's no any other shift. And so on. So here we have only things that are shifted in -2 and nothing else. And if we believe this pattern, then this algebra is going to be Koszul. But this already tells you something like morally important, that testing if an algebra is Koszul is, in general, is infeasible, it's impossible, because we are looking at a resolution that is not finite. So either we find stronger criteria or we just can't do it. And there are actually algebras, there are examples of algebras which fail the linearity, so whose residue field fails to have an R linear resolution in arbitrarily high homological degree. So it's not that you can say, yeah, I checked for high enough homological degree and now I'm good. No, this is not going to work. Yeah, there's a couple of examples of classes of rings which are Koszul. For example, if you take something called the segret products of two Koszul rings, this is gonna be Koszul. Veronese algebras are Koszul algebras. And for monomial ideals, monomial algebras, so algebras defined as a quotient of a monomial ideal, these algebras are Koszul if and only if they are quadratic, so defined by monomials of degree 2. And actually being defined by an ideal generated in degree 2 is a necessary condition for the algebra to be Koszul. So this is what I'm stating in the last line of this slide. So R is Koszul and R is of the form S mod I, implies that the ideal is generated in degree 2. And actually,
can I ask something, Lorenzo? You mentioned before in the about that it's hopeless to say if some ring is a Koszul, let's say face ring, Stanley-Reisner ring. So complexity, from computational complexity point of view, is there a statement to say here?
Well, for Stanley-Reisner rings, it's actually trivial because those are defined as a quotient of a monomial ideal. So actually a Stanley-Reisner ring is Koszul if and only if the simplicial complex is flag.
Right, but for other homogeneous ideals?
For other rings, I don't think there's any statement. And the reason is, I think it's precisely given by these constructions of algebras which fail the Coszul property in arbitrarily high homological degree. I don't know if there's any complexity class has been studied about it, but I would say that's a pretty strong obstruction for anything nice to happen.
Okay.
Yeah, maybe there is. Yeah, maybe there is hope for other special classes. I don't know, binomial ideals or things like that. But yeah, and nothing is known in general. But it's interesting that you ask, because we are going to construct a bunch of algebras for which we can control the Coszul properties.
Okay, thanks.
Thank you. And yeah, and this is the algebras that we are gonna get at the end of the day, at the end of the construction. So this slide is again is a little technical, but if you feel like taking a break, maybe this is the right moment, because in the next slide I'm gonna present a combinatorial description of the same algebras, which does not assume any abstraction that is appearing here. But for the sake of completeness, I think it's important to understand where this comes from. So it comes from the work of Nagata, who in the 60s studied a procedure to turn submodules of an R modulus M into ideals of a certain new ring called R tilde. This process is called idealization because it turns something into ideals. And it can be applied to general modules M, but we're gonna make a specific choice. So we are gonna use as the module M a shifted copy of the canonical module of R, okay? Again, this is another piece of detail that I'm sweeping under the rug a little bit, but a canonical module is a module that you can associate to Cohen-Macaulay rings. So if you remember the minimal free resolution that I had on my slide, we said that we didn't say that, but it turns out that there's a functor that you can use to apply on this map, on this sequence, and it's gonna flip all the arrows. Now, the Cohen-Macaulay property guarantees that when you apply this functor, you still get an exact sequence. Now, the question that you can ask yourself is like, what is the module sitting on the left such that the new sequence that I obtained is a resolution for this module? And this is exactly the canonical module. The shift, you shouldn't worry about the shift. It's just shaped in a way that is generated in degree 1, okay? And this is already telling you something, because because I am shifting with one number, and I can guarantee that the canonical module is generated in degree 1. This means that I knew that the canonical module was generated in a single degree before. And this is hidden in the level property that I briefly mentioned. So when the algebra is level, the canonical module is generated in a single degree. So this means that I can shift it and I can make sure that it's generated in degree 1. And then the new magic ring, R tilde, is defined as a semi-direct product. So the semi-direct product is nothing more than the direct sum as a module. But the product structure is defined in a little bit of a funny way. So on the first component is simply the product. But on the second component, you get this cross product, some type of thing. So R times B plus S times A, okay? And it turns out that there's a very precise relation between the R tilde resolution of the field and the R resolution of the canonical module. So you can write the corresponding Poincaré series as one as there's a formula as a rational function, one or the other. And something that you have a very good control of is the H vector of this new algebra R tilde, because it's the mirror sum of the H vector of R. Well, by mirror sum, I mean is the ith number plus the s minus ith plus one number. So what you have to think is that I take the H vector of R. I am hand waving a lot. You basically duplicate it and shift it by one and then mirror it. Okay, so duplicate, shift by one, and mirror it. So I don't think it's at least impossible to believe that the sequence that you get at the end of the day is palindromic. So it's a sequence of symmetric sequence of integers. And it's not a coincidence, because it has been proved by possibly more than the references I mentioned, but at least by Gulliksen and Reiten, that if you play this game with a standard graded and level algebra, then the R tilde algebra that you obtain by idealizing with respect to the canonical module is Gorenstein and standard graded. So this is a machine to turn R into a Gorenstein algebra. Okay. This is assuming that R is, okay, standard graded. This is not too restrictive, but level. Level is, it is a pretty restricted condition. But we've already seen an example of something that is level. Namely, the Stanley-Reisner ring of the beer ball of delta. So if I take delta, any simplicial complex, I take the beer ball gamma. I consider the Stanley-Reisner ring of gamma. This is standard graded and level. This means that I can apply this machinery and obtain a Gorenstein graded algebra. This is exactly what I will denote with R of delta. So we choose this notation, R sub delta, because we want to stress that the dependence is really on delta. The gamma, the beer ball, it's just a construction step. The dependence is actually on delta. Okay. I hope you are not too confused by all of this algebra, but now it comes basically an explanation of the same object, but through a combinatorial perspective.
Sorry, before going on, so what is S here in the, when you have the H vector of R tilde? So you have H
oh yeah, thank you. S is the length of the H vector.
Okay.
So, or the degree of the H polynomial, the Sokel.
Thank you.
Yeah, you're welcome. Yes, and now we give a combinatorial presentation of the same algebra. So if you are not too keen on canonical modules and other mysterious algebraic objects, this is perhaps the place where you can get back on track. So we said that if we consider any simplicial complex, beer ball idealization, then we obtain a Gorenstein graded algebra. And this is how it looks like. This is a presentation of this algebra. So we present it as a polynomial ring in, well, 2n variables. N is the number of vertices of delta. So there are the variables xi, yi for every vertex. And then we pick a variable z sub f for every facet of delta. So the number of variables is twice the number of vertices plus the number of facets of delta. And the defining ideals are a bunch of different things, but all very combinatorially nice ideals. So first we have the Stanley-Reisner ring of delta in the x's. So the generators of the Stanley-Reisner idea are in the variable xi's. Second, we have the remaining piece of the generating set of the Stanley-Reisner ring of gamma, namely the products xi times yi. Then we have the square of the ideal of the variables corresponding to facets. So the square of the ideal corresponding to the variables z sub f. Okay, now let's keep those three pieces in a corner. The interesting bits are two ideals, A and B. The first one is a monomial ideal and is generated by monomials of degree 2. And they are constructed in the following way. So the product xi times z sub f for every I not in f. Okay, so I go through all the facets and I pick the variable z of f, and then I pick all the vertices which are not contained in the facet f, and I build this product. So these are monomials of degree 2. B possibly is even more interesting because it's a binomial ideal and is defined as follows. So we pick pairs of facets of delta, and we construct binomials of the form y f1 minus f2. This simply means all the product of the y variables which are in the facet f1 but not in the facet f2 times zf1 minus the same thing for f2. Okay, let me briefly repeat this again. So we pick pairs of facets, and then we consider all the elements which are in f1 but not in f2. We take the corresponding y variables, multiply them. We multiply with zf1, and then minus, and we play the same game with zf2. So these are binomials, homogeneous binomials. They are pure, so they have coefficient +1 - 1. And they can have arbitrarily high degree. You might agree that, for example, if you take two disjoint facets, well, the degree is going to be pretty high because there's a lot of y variables that are in f1 but not in f2. Yeah, I should definitely mention that we obtained this presentation by using a result of Mastroeni, Schenk, and Stillman. So they consider idealization for other purposes and gave like a general description, which we translate in the language of Stanley-Reisner ring and obtain this presentation. These generators are actually very nice. So they form a universal Grobner basis, not only a Grobner basis, but a universal one for every term order. And actually, after we wrote the first version of our article, we realized that a similar algebra had been studied by Gondim and Zappala. I say similar because it's actually an Artinian reduction of this one. But it's interesting because they don't arrive to the same conclusion with idealization, but with a technique called apolarity, which is also a well-known technique to construct Gorenstein algebras. Yeah, let me see how am I doing on time, even though it's fairly flexible, as I understood. So here's an example. I will consider the delta to be the boundary complex of the octahedron, so the three-dimensional cross polytope. This is the Stanley-Reisner ring. So this is the Stanley-Reisner ideal. And now we construct the algebra R of delta. So we have 6 + 6 + 8 okay, variables. Should be 20 variables. 6 for the vertices and 8 for the facets. And then the ideal defining this algebra is the sum of these pieces. Again, I ask you to don't worry too much about the first three. The first three are fairly easy to understand. Let's focus on the last two. So why is x2 z135 there? Well, 135 is a facet and 2 is not in 135. So this was the first rule that I gave you to produce the monomials of degree 2. Now let's get to the binomials. Y is y5 z135 minus y6 z136 in there. Well, 135 and 136 are two triangles. They intersect in 1, 3. So if I take the difference of the first with the second, I get 5. And then I write y5 times the first minus, if I take the difference of 136 minus 135, I get 6. And that's why we get y6 and z136. And here I wrote a couple, and you see that the degree is can actually be very high. So here there are generators of degree 4 corresponding to facets which are disjoint. But it turns out that if you are after a minimal presentation, you can generate this ideal only using elements of degree 2. Okay, so this presentation, sorry, let me go back one step. So this presentation with monomials, with binomials of high degree was not minimal. And if you look at the minimal one, they all have degree 2. And this is something that we are very interested in, because if we want to study the Koszul property, a necessary condition will be for the algebra to be quadratic, so to be generated by elements of degree 2. And here is the main result that we obtain. So we completely characterize when the algebra is quadratic, so it's generated in degree 2, as the field as an R-step linear resolution over the algebra. Most probably the most interesting one, the algebra is Koszul over the field. And there's an extra one that I will fill in the next slide. So how do we characterize that? Well, it turns out that the algebra is quadratic if and only if the simplicial complex is S2. So remember, S2 means pure, and connected. The links are connected for all faces of codimension higher than 1. This is a property that the octahedron satisfies. So it's good that we found a quadratic R of delta for that. Well, a natural extension of this property is that delta satisfies SER property as SR over K. And this happens if and only if the field has an R-step linear resolution. The protagonist of this theorem is that delta is Cohen-Macaulay over K if and only if the algebra is Koszul over K. So for this class of algebras, we do have complete control of the Koszul property, and it can be checked with the same effort that one needs to check that delta is Cohen-Macaulay. So these properties are all in increasing strength. And yeah, this is precisely what I said. So we can control the Koszul of the Koszulness of R of delta. And in particular, since until not so long ago, like 10 years ago, probably, there was this question in the literature if any quadratic Gorenstein algebra was actually Koszul, until examples were found, probably less than 10 years ago. So with this machinery, we can actually generate a lot of Gorenstein quadratic algebras, which are not Koszul, simply by starting with simplicial complexes, which are S2 and not Cohen-Macaulay. And yeah, let me just mention that this is not the first time in the literature where the word Koszul and Cohen-Macaulay appear together in a statement. So although this case is not contained and does not contain any of the instances that I will mention here. So something similar has been proved for semi-group algebras by Peeva, Reiner, and Sturmfels. This has been, has been proved for incidence algebra of posets by Paul and Woodcock. And I recommend also an article by Reiner and Samate in which they sort of generalize these two approaches. And on a very abstract and way more general level, it has been studied by Bruno Valette on properties of operads and their associated posets. So this is a very, very abstract algebra type of result. Okay. Let me see how am I doing on time. Yeah, I think I will skip the proof idea and eventually get back to that if there are questions. Now let me fill in the last gap in the main theorem. So if you remember, the last property for the simplicial complex was the Cohen-Macaulay property. So now let me give you something stronger than Cohen-Macaulay. So this property is shellability. I will say that a simplicial complex is shellable. Pure simplicial complex is shellable if I can order its facets in a way that whenever I intersect the ith facet with the simplicial complex generated by the first I minus 1, I get something that is pure and of codimension 1. Okay. Sorry. So here's a picture. I'm going to start with a triangle. I attach a second, a third one, and you can see that the intersection between the new and the old triangles is this black edge. And again, this black edge. So this is codimension 1 and pure. So we are doing fine. And then here I make two choices. So if I attach this triangle in this way, then the intersection is still pure and codimension 1. So I am still shellable. This is a shellable complex. But if I attach the triangle in this other way, then the intersection is two disjoint points. So it is pure, but it's not of codimension 1. So this is not shellable. Okay. So shellable complexes are Cohen-Macaulay, and they are actually Cohen-Macaulay over any field. So let's assume I want to put delta shellable as the last condition for my main theorem. On the right side, there should be a condition that possibly depends on an order, but it certainly, or the existence of an order, but it certainly does not depend on the characteristic of the field. And this is having a quadratic Gröbner basis. So we proved that a delta is shellable if and only if R of delta has a quadratic Gröbner basis. Okay. And so we actually have, there's a very tight connection between the term order on R of delta, which gives you a quadratic Gröbner basis, and the order of the facets that certifies shellability. So in particular, R of delta will have like a quadratic Gröbner basis for every term order, which is, we say, compatible with the shelling. So if a facet variable comes before another, then the facet Fi should come before Fj in the shelling order. Okay, so this is the main theorem. Now I will conclude with two, let me say, applications. So two interesting results that we can obtain as corollaries. So the first one is, it's a statement that I like a lot. So if you give me, you can give me any finite list of primes, prime numbers. Then we can construct quadratic algebras that are Koszul over K, if and only if the characteristic of the field is not in the list of primes you gave. Okay, it was known that well, yeah, that these objects might exist. Actually, maybe not. It was never stated for any list of primes, but it was known that to the expert that these things existed. But there was never a recipe to construct such. And the way we obtain this result is simply by finding the right simplicial complex and then applying the main theorem. And the right simplicial complex is any flag triangulation of a length space. For example, this is one choice. This is not the only one. Because length spaces have this interesting first homology group, ZP. So in particular, the vanishing or not of the, so the Cohen-Macaulay property for these simplicial complexes is going to depend on the characteristic of the field being or being not P. Okay, so in particular, it's Cohen-Macaulay if and only if the characteristic is not P. Okay, but this is a single prime number, but it's not a big deal to do the same game for more primes by taking the connected sum. So basically, connected sums of flag triangulations of certain manifolds, if you apply this idealization game, that will give you algebras which are quadratic and whose Koszul property depends on the characteristic being or being not in the list of primes that you gave me. Of course, this is, well, it's constructive in a sense, but these algebras will have huge codimension because it depends on flag triangulations of length space. And in general, there's no machinery to triangulate these manifolds in a flag way with few vertices. So these algebras are going to be huge, but they do exist, and we can like explicitly detect them. And finally, is again, it's something about the numerical invariance of those algebras. So let me remind you that Gorenstein algebras, such as the algebras R of delta, they do have a palindromic H vector, or if you wish, a palindromic H polynomial. This is just a reminder of what I mean by that. But then, instead of writing them as in the monomial basis, 1 t to the first, t to the second, and so on, we can use a more compact basis, which is defined in this way. So we can use these palindromic polynomials. And I say more compact because these are actually roughly half many as the monomials t to the I. And this new expansion defines coefficients gamma I. Okay, so it defines integer coefficients gamma I, which a priori, they are integer, but they can be either positive or negative. And this sequence is called the gamma vector associated to the palindromic sequence H, which is the H vector. Okay, so this vector is has attracted a lot of attention in relation to flag spheres. So the Stanley Reisner ring of a sphere is Gorenstein. So it has a symmetric or palindromic H vector. And here I just mentioned two conjectures, but there are actually more. So one is by Charney and Davis. For that, we restrict to odd dimensional spheres. So D is even. This conjecture predicts that this is the last gamma number, is non-negative. So it might look innocent, but it's actually a very deep conjecture. It's a very important one, has been studied a lot and proved in certain specific cases. And it has been generalized by Gall in 2005. So Gall's conjecture predicts that the gamma numbers, oh, by the way, when I write gamma I of K of delta, I mean the gamma vector associated with the H vector of delta. Maybe that's not sufficiently clear. That's what I mean. And Gall's conjecture predicts that these numbers are all non-negative. So that when I apply this funny transformation to the H vector of a flag sphere, I obtain a gamma vector which has non-negative edges. And this has been strengthened. For example, Eran with Peterson, they have a conjecture that for flag spheres, this gamma vector is actually the F vector of a simplicial complex. And they also have further strengthenings on the type of simplicial complex that this gamma vector is the F vector of. So what we do is we found this question in the literature. Does any Koszul Gorenstein graded algebra with H vector from H0 to H2E, so it has odd length, satisfy let me say, the Charney-Davis inequality. So satisfy the fact that the last gamma number is non-negative. Okay, this was posed in a paper by Peeva and Stillman. So basically, this is, in a sense, is a generalization of Charney-Davis, because here we are not restricted to the Stanley-Reisner ring of a sphere. Here we are asking if the same property is true for every Koszul Gorenstein graded algebra. So this strictly contains Stanley-Reisner ring of flat spheres. So what we do is we study the gamma vector of our R of delta algebras, and we prove the following formula. Now the formula is, as often in combinatorics, is pretty messy. There are binomials. There's a lot of things, but this is actually a sum of, these are positive numbers times hk of delta. And then there's a sign in front of it, which only depends on I, okay? So in particular, if you were to handle a simplicial complex delta for which you know something about the sign of h of k, then you know everything about the sign of gamma I. Okay, and yeah, to obtain this result, we simply use like combinatorial manipulation and the fact that we know that the h vector of R of delta is the mirror sum of the h vector of gamma, and that we know that the h vector of gamma depends on delta in some way. Okay, but this is enough to answer the question, and the answer is no, and it's no it's a pretty strong no. Because, for example, if we consider delta to be a Cohen-Macaulay complex, so that these numbers are actually non-negative integers, well, then the gamma numbers, the gamma vector of R of delta is alternating in sign. Okay, so in particular, we can find a choice of D being the dimension of delta plus 1. This choice it's actually weird, but not weird, but so when D is congruent to 3 mod 4, then the Charney-Davis inequality is not satisfied. And it's not only not satisfied, this number, it can be as negative as we want. Because when if we choose delta to be Cohen-Macaulay, then this number is actually -2 times the top of homology of delta. So we can take, for example, a flag triangulation of a wedge of spheres, and this is gonna give a hugely negative Charney-Davis quantity. Okay. Yeah, let me conclude. This is the very last bit. Indeed, if we take the 3-dimensional cross polytope, so the boundary complex of the octahedron, this is a flag Cohen-Macaulay complex. This is its F vector. This is the H vector. We can use the control on the H vector of R of delta to write down explicitly how it looks like. And then the associated gamma vector has a -2 at the end. Okay, and this -2 comes from -2 times the fact that the top homology group of the sphere is one-dimensional. Top homology vector space is one-dimensional. Okay, I think that's everything I wanted to tell you. Thank you for your attention.
All right. Thank you very much for your talk. Are there any questions?
Yeah, so, okay, may I ask?
Sure.
So after you started from delta, a simplicial complex, then you constructed these algebra of delta. And then can you proceed by some, say, Grobner basis procedure or something like that to get back a new simplicial complex that will somehow have a similar enumerative properties to say those of R delta.
I see. Well, yes, we definitely can, but I think maybe I'm wrong, but a reason why you are probably interested in this like extremal numeric property is that you would like to have a sphere as a simplicial complex, or
yeah, if you can really have, say, for example, a sphere with its gamma is the same as the gamma of the R delta, then okay, you will have counterexample.
Yes.
But maybe if it's not a sphere, maybe some.
No, I mean this. Let me go back real quick. Where was I? Maybe this is good enough. So the generators of the ideal here are actually a universal Grosvenor basis. So this means that you can fix your. Oh, I see what you're saying, because there are squares here. Yeah. Well, you can probably polarize those in a way, but yeah. So I still think you can easily like find a square free. Maybe after polarizing, yes, you can find a square free initial ideal, but there's gonna be no control on how the simplicial complex looks like. I think that is hopeless with the techniques we have so far.
No, maybe look, for example, if you start with a complex, then you can do this algebraic shifting of Caulay, for example, and then get a new simplicial complex with some simplified combinatorics. And then maybe here you can also have some canonical way how to take a Grosvenor basis and get a new complex from the complex you started with. Maybe it will be interesting. I'm not sure.
I see. Oh yeah. That would definitely be interesting. So you're saying delta, and then shift, and then gamma,
no,
and then
delta, then R delta, and then do some Grosvenor basis process or to get back a simplicial complex.
Okay. That's very interesting. We clearly haven't thought about that, but yeah, that's very nice.
Are there any other questions or inputs? There is something in the chat from Leo Chan. For Koszul R delta, is its Koszul dual Gorenstein?
Oh. So it's Koszul dual Gorenstein. Well, no, I want to say no, but it doesn't have to be the case in general, I think. So the question was if the Koszul dual, so when R of delta is Koszul, is the Koszul dual Gorenstein?
Yes, that's the way I understand it, yeah.
So now, again, I don't have the answer, but I would like to answer no. So of course, there is this relation, right, between the Hilbert series and the Hilbert series of the dual, which will tell you that the Hilbert series of the dual is something like 1 plus t to the d divided by a polynomial that is not quite palindromic. I mean, it is, the absolute value is palindromic, right? The alternating sign. But I don't think it has to be Gorenstein in general. I will look into that, but I don't think so.
Okay. Are there any other questions? That doesn't seem to be the case. So thank you again, Lorenzo.
Thank you.